All right. Welcome to this last session of today. It's again a session focused on methodology and applied to the case of myocarditis associated with COVID-19 vaccination. My name is Olaf Klungel and I will chair this session. And it's a pleasure to invite Anders again. Anders Hviid is a professor at State and Serum Institute and chair of the Department of Epidemiology Research. And please.
Thank you. Myocarditis, yeah. I feel like I've done a lot of myocarditis studies, COVID-19 and vaccination and myocarditis studies now. I just counted inside my head. We did a Danish one where we focused on myocarditis diagnosis with troponin values using lab database. So we did a Nordic version in adolescents and adults of vaccination and myocarditis. We did a study of the prognosis of myocarditis after vaccination. We've done this one in the context of EMA, in myocarditis in children and adolescents. And then we've done a study also focusing on the first Nordic collaboration study was on dose 1 and dose 2. It's very far back in the pandemic by now. Then we also did one Nordic study looking at the booster. I just checked, pro tip, never submit anything to European Heart Journal. If you know that journal, never submit anything there. We submitted that paper in December 2022. Last week I got a major revision back from them. So I don't know when the booster paper will be published. So this was the study in children and adolescents. Right, and as I mentioned before, looking at children and adolescents, we were able to have a combined cohort size of 5.1 million. We did 3 different statistical or methodological approaches. We've heard about some of them today. You can also call that a kind of calibration approach or a way to indirectly assess different types of biases and confounding. We did a contemporary cohort analysis, right? The traditional approach when you have a whole population, the contemporary cohort, and by contemporary I mean we compare the vaccinated to the unvaccinated or the less vaccinated in the same periods, more or less, like in the period where people are eligible for COVID-19 vaccination, right? Then we have the self-controlled case series method, which most of you are probably also familiar with. We've heard about a special case of that today, the self-controlled risk interval method. It also has some nice properties. I'll get back to that, I think. In our setting, of course, it's nice that you can do this self-controlled case series method nested in your big cohort. So you start with your big cohort and then you choose to do like a self-controlled case series nested in that cohort using the cases that you also have in your contemporary cohort analysis. Then we did a third version, which is the observed versus expected, which is basically also comes easily when you have the whole cohort. You use basically the follow-up time in the vaccinated and compare that to historical rates, right? Since Pfizer-BioNTech was the most used vaccines in children and adolescents in the Nordic countries, that's what we looked at. Again, it's really important to remember that also when you talk about fancy calibration methods and emulated target trials, these are very rare events, especially in children and adolescents. So we really also need to consider, I don't want to throw away the traditional methods that perhaps are better at preserving statistical precision. Yes, and then we have this main risk period, 4 weeks. This is, of course, also something you can discuss. It's not data-driven, it's more or less just pulled out of a hat, really, initially. You have this idea that acute, causally related vaccine safety events occur in the weeks after vaccination. But whether you use 2 weeks or 4 weeks or 6 weeks is a little bit random sometimes. So other differences, of course, is that in the contemporary cohort analysis, you would traditionally be able to use more sophisticated adjustment control. The self-controlled case series analysis, as we heard, has inbuilt confounder control by those that are time stable. In the observed versus expected, you are usually not taking that many potential confounders into control. It's a little bit of a quick and cheap method. And so it typically would be like age and sex that you take into account there. This is again just to emphasize that we are in this large cohort setting. That's where we start, and that's where we can sort of nest all the other designs in. These are the follow-up. We start follow-up when people are eligible for vaccination, typically. Then they are followed until they are vaccinated with 1 or more doses, right, or until we end follow-up. And in the contemporary cohort analysis, this becomes then a comparison of these risk periods to unvaccinated follow-up among people who become vaccinated, and then the minority group, right, the truly unvaccinated, who are probably very weird people, those who remain unvaccinated throughout the COVID-19 pandemic. And then the self-controlled case series method, we are essentially up here just using this type of information, this timeline for the cases, right? And in the observed versus expected, we are also up here, we're using these observed rates and comparing them to historical rates. These are the results for the relative risks from the 3 methods. For the myocarditis association, I should say that there was a lot of other outcomes in that EMA study. Also the thromboembolic outcomes and the immune-mediated diseases. You can see the results for 1, 2, and 3 doses. What's reassuring, in particular, if we look at dose 1 and 2, is that the methods are more or less giving the same answer, right? And there also isn't any sort of big discrepancies in the statistical precision. When we get to dose 3, we see larger differences, especially between the self-controlled case series method and the other 2 methods. I should note here that, and this is again a challenge when doing these multi-site studies on very rare adverse events, that not all countries were able to contribute to the 3-dose association analysis, because 3 doses were not that common in these young age groups. That's probably also a very special group, right? So I'd put most stock in the 1 and 2 dose results. It's interesting, I think, that compared to some of our previous work, that we saw a larger effect after dose 2 in the previous work. Right here we see both similar effects after dose 1 and dose 2. The self-controlled case series, and normally, if I am to speculate, it's probably due to this violation of becoming a case shouldn't influence future propensity of vaccination. I would hazard, if I should guess, right? reassuring that they give more or less the same answer, all three methods, I think. Absolute numbers. This actually, also in our previous work, we came to that conclusion that this was actually the most interesting, right? It wasn't so much whether the relative risk was 3, 4, 5, 7, or 10. It was what is the absolute risk of myocarditis, especially taking into account the specific age group and actually also sex. Here I only showed the results stratified by age group, and you can see that the absolute risks and implications are different of these associations, and that's what most of the discourse has really been about with respect to this myocarditis signal. Has been the absolute risk. Is the absolute risk of myocarditis greater after vaccination than after natural infection? That has been very controversially, hotly debated, right? And also a very, very difficult question to give a good answer to. Yeah. So, I mean, if you should recommend anything, it's really to do to use methods that are good at giving you some absolute risks. Then again, some of the challenges that we've had with respect to this meta-analysis report, again, I'm coming back to the very rare events, is that it's a problem when not all countries are able to contribute to a specific association estimate, right? Because we're looking at short risk periods after vaccination. So where are you most likely to miss the information? That will be where there's no cases, right, in the main risk period. And so you will tend to overestimate the association when you don't get these contributions from sites. So when you compare the estimate that you would get by pooling the data to the estimate that you get by doing the meta-analysis will tend to overestimate. And this becomes an even greater issue when you have to go into these strata in these comparisons, where you have to go down to a very narrow age strata and sex strata, right? Then the problem becomes even bigger in these analyses. The classical self-controlled case series analysis, this main assumption that being a case shouldn't influence your probability of getting vaccinated after being in case, it's always violated, right? I mean, to some extent. The problem is just whether it gives measurable bias, right? And we use the pre-risk period, or we can compare periods after vaccination to try to take into account for that. There's also been some development here. There's this event-dependent exposure calibrated version. We were not able to, in a timely fashion to use this. My sort of intuition says that it's a little bit less statistically efficient. Maybe there's someone here who can say more to that. Or otherwise, why wouldn't you use this method that takes event-dependent exposures into account all the time, right? Then there's another really important issue with myocarditis is that, as I mentioned, infections also cause myocarditis. And so you also need some good data on infections. Very few countries actually had good data on infections. And you also need to think about how do you count your myocarditis cases. For example, I think we chose to censor at infection, which means that you miss out on the infection-caused myocarditis cases, for example, in unvaccinated, right? And that might also be a problem. And you have to take that into account in the interpretation. So, yeah. Let me see if I have anything else. No?
Thanks, Anders, for very concise and clear presentation on the myocarditis studies in Nordic countries. There's time for some questions. Vera?
Thank you so much. The Danish data is close to my heart. I have two questions, actually. When you say that in some countries you have rare events and you cannot estimate some associations, do you mean you have 0 exposed cases? Or?
Yeah.
Okay.
Yeah.
And do you think, I mean, this is information, right? It means it's
yeah,
a safety...
we're throwing away information by not being able to produce a country-specific estimate and only doing the meta-analysis on the country estimates that have exposed cases. Yeah.
I'm just wondering if we shouldn't include the 0 case scenario because it means it's...
We should if we could, but the way we've set it up, where we are not combining data, but only combining estimates, we're not able to do it right.
Yeah. It's just amusing because with 0 is information which you want. It means it's safe, right?
Exactly. Yeah.
But and another question is: do you know approximately the magnitude of the risk in the COVID infected myocarditis?
It wasn't that big in the Danish data, and I mean, I think also it will tend to with more people being more vaccinated, having previous infections without myocarditis, and then the later variants, the whole picture changes all the time. It's a very dynamic situation, very difficult to say anything very concrete about.
Thank you.
All right. So the self-controlled case series and the different assumptions I think we'll discuss in later presentations. I was wondering about, because you present now nicely the results of the different studies with the different designs, but you did not start off with all the different designs. They were done separately, I think. What were the considerations for doing each of these studies? And it's nice to see actually the consistency of the different approaches, but you decided, I guess, one by one when you would do such a study, in which situation?
Yeah, I think the first study we did was a purely Danish study where we used, as I said, diagnosis plus troponin measurements. There we did a cohort study and a self-controlled case series as a sensitivity analysis, and they matched well. And then maybe I'm misremembering, but in the first combined Nordic, we just did the contemporary cohort because we were under a lot of time pressure.
Yeah. So different practical reasons to do
a lot of practical reasons for why we did what we did. Yeah.
Okay.
Yeah.
Great. Thanks. Any final questions for Anders? No. Well, thanks again so much for being here, presenting here 2 times actually.
Yeah.
Does he get 2 pepper nuts bags? Thank you. Right. So our next presenter is Carlos Durán. Carlos is an assistant professor at the UMC Utrecht, and he will talk to us about the myocarditis study methods from the CVM study.
Well, good afternoon again. Just to say that this presentation was prepared together with Miriam and was initially presented in Halifax this year in IGPE. And also I want to acknowledge the huge amount of work of Sophie Bots and Svetlana on these particular results. Well, the disclaimer, as always. Then a little bit of context and background. Well, in COVID-19 vaccine monitor study was also aimed to produce rapid assessment studies to support the decisions by the European Medicines Agency. So it was the readiness phase that was presented in the morning, but also was thought to have data ready to rapid assessment studies. So we received the initial request around myocarditis in September 21, and we published initial results in a peer-reviewed journal where we showed an increased risk of myocarditis for mRNA vaccines, especially after dose 2, and some effect modification by age, and also, and the risk also was elevated for ACIDs, but not significant at that moment. So, of course, we needed to perform periodic updates to confirm to monitor the dose effects. So, in this updated analysis after the publication, then we really went into a self-control risk interval using vaccinated cases of myocarditis only. In the first publication, we used also pericarditis, and was also a paper using also a cord design. Then the exposure was the first, second, and third dose of Pfizer, Moderna, AstraZeneca, and Janssen vaccine. The outcome was myocarditis through diagnosis codes. And we perform a conditional post-analysis adjusted for calendar time. We perform meta-analysis, and we did a sensitivity analysis using weekly risk windows. And then stratifications by age, under and above 30, and by gender. So this is the study diagram. Self-control risk interval was also presented by Sophie in the morning, but this was the classic, you see the control window, the risk windows. We used 28 days after every single dose. So I go. In this, this was the first analysis what we published, and these are the numbers what happened in the updated analysis. So several of the databases already increases the follow-up time, and also we included a new database for this new analysis, Visabio. This leads to an increased number of almost 9 million people for the analysis, and a bit less of 100 new cases in risk and control windows myocarditis cases. So results, you see that for Pfizer it was already identified a significant effect for those two, not for dose one, but for those two. In Moderna it was again those two, and a bit of higher estimate for AstraZeneca, but not significant. And for Janssen it was too wide the confidence interval. This was for all doses and ages. So then we go to the sensitivity analysis by weekly periods. So you see here that then the first dose of Pfizer became significant in the first and second weeks. Also again, the second dose in the first week. Then for Moderna, it confirmed the second dose the first week, and also the fourth week of the second dose, but you see the confidence interval is very wide. But then it also became significant with AstraZeneca for first dose, and in the second week, and in the second dose in second week as well. So when stratified by age, then we have under 30 years, over 30 years, and then you see again the trend of Pfizer dose 2 as significant, and also Moderna dose 2. Yeah. Then this was also performed in the new analysis. It was excluded the COVID vaccine disease, I mean people with positive diagnosis of COVID-19. And again, you see for Pfizer, dose 1 resulted significant. For Pfizer, dose 2, Moderna, dose 2 significant. But also AstraZeneca became significant after excluding those COVID-19 cases. So conclusions. Well, we confirmed the increased risk of myocarditis following second dose of mRNA vaccines using a 20-day risk window. with the highest risk in younger persons. Then the new observations on this new and this updated analysis that myocarditis seems also associated with adenovirus platform vaccines, but let's say different patterns and different age dose pattern than mRNA vaccines. And interesting, this was already presented or published by Patton and colleagues. I think it's in one of the subsidiaries of one of the Nature journals. This is already published. Those three of Pfizer COVID-19 vaccine is not associated with an increased risk of myocarditis in either below or above 30 years. I think we didn't take a lot of attention to this, but here you see those three. It really goes down in Pfizer, but it goes up in Moderna for under 30 years, even though it's not significant, but it's really a different pattern here. And what I just said, for Moderna vaccine, the risk is elevated, not significantly, after those three under 30 years, but not above 30 years of age. And then finally, those brand, age, and gender variations require large sample size to be able to study the effect. I mean, this is the most important thing. We want to explore this, then we need more databases, we need more larger databases to study further this the effect of those in brand and age. So I think this is my last slide. Yes, of course, thank you for all these people who contributed to this work. And I don't know if Sophie or Lana or Miriam, you want to add something that maybe I missed, but otherwise, thank you. Yes.
Thank you, Carlos. Any questions from the audience or additions from the co-authors?
Yes, thank you for the nice presentation. I wondered, when you exclude the COVID-19 cases, you exclude them like just if they get it during the study period, but could you also have excluded just the time after the COVID-19 diagnosis?
I need you to repeat the question, please.
Yes, so it seemed like you excluded everyone who got COVID-19, and it seemed like you excluded them for the entire study period, but could have been a possibility also to just say you stop following them after their COVID-19 disease?
Yeah, it's a possibility, but maybe I will need more methodology background for this.
This is what we did, actually. I think we excluded person time.
Person time after, no?
Yes.
Yeah. Thank you.
Thank you.
Yeah, I think we need to now, Sophie.
Other questions? Maybe about the those three Pfizer. So we just saw the Nordic country results with clear increased risks, I think. So we didn't find it here. Any potential explanation? Maybe we will come to that in a later presentation, but any thoughts from you?
I don't have it, but...
It would be worthwhile to look at the distance.
Yeah.
The distance between the doses, it was on one of the slides, like the number of days. But I think in the Nordic countries, probably they started vaccinating faster at least. Or the delay between the second and third dose was less. So that's one of the hypotheses, no? That it's, you accumulate doses and then if you have longer distance, I think that's what they do in the US now, they distance more, so...
Yeah. Because the average time between dose 1 and 2 is around 40 days, but between those two and booster is 200 or even more days. So, yeah.
Thank you. Last question, Saad?
There's a
Comment
question
on,
also here.
comment on your comment, Olaf. Isn't it that fewer younger people had the third dose? And it's a condition of young people, because the third dose and the booster was more commonly taken by older people.
Yeah, we would have to look into the data if that's right. Yeah, I can't give you the answer. Okay, thanks, Carlos. One more? Yeah.
Thank you. It was actually the same question. How is it that you stratified data by age 30? Because in previous studies we observed that mostly it happens and the risk difference is mostly significant in age in adolescents under 17 years old. So why you stratified based on?
It was done in the beginning, and the paper we published. It was done in that stratification. In the beginning, it was just a matter of exploration, and we just decided to keep that. But there's not really a strong reason for that. But it's true that it really helps to see an effect modification by age.
Yes. Thank you.
Thank you.
Thanks, Carlos. And then I welcome Anna Schultze to the stage. Anna is an assistant professor at the London School of Hygiene and Tropical Medicine, and she did a lot of work on self-controlled designs within the CVM project, and she's going to talk about the impact of different design choices on the results.
Thank you. Okay, brilliant. So really nice to be here presenting this today. So I had quite a long title, but essentially what I'm going to be talking about is whether our study designs matter. And I'm particularly interested in self-controlled study designs. So I'm going to be presenting results from this comparison we did of 4 different types of self-controlled studies as part of this work. So I think we've already heard today, self-controlled studies are really useful. There's no control group, you don't have to identify one. It automatically controls for confounding. We've seen before, I don't think I have to go through the self-control case series. We select cases, define a risk period. And then in the SCCS, all time, I don't know why my slide is doing that. All time that's not risk time is used as kind of like a baseline reference period. And then in a variant of the SCCS, the SERI, which we've seen presented earlier, you use just some of the time as the reference time, so you can use time either before vaccination or after vaccination. And we've heard before that the self-controlled study designs are nice, but they have certain assumptions. In particular, we were interested in this first one, so we heard Anders set the scene really nicely earlier, saying that probably when we study vaccine safety, we don't think that this particular assumption, that the occurrence of the safety outcome shouldn't impact your probability of later getting vaccinated, really holds true. So what can we do if we violate this assumption? So, what happens? So essentially what happens in this scenario is that we have a lower probability of observing these cases with events right before vaccination. So we underestimate the risk of the event in the reference time, we overestimate the harm of vaccination, and in this scenario we were particularly worried because we'd used an SERI where we used reference time only before vaccination. So we were essentially worried that in the core studies we'd potentially overestimated the harm. So how do we fix it? Well, we can use pre-exposure periods, which is essentially when we remove a little chunk of time right before vaccination from the reference time. But we can only do this if the delay is short-lived. We can use only post-vaccination time as reference, and Anders alluded to this as well, but this only works if we have a single vaccine dose. It does not work if you have multiple vaccine doses. So if you have multiple vaccine doses, we have to use these slightly more advanced methods. So there's something called a truncated self-controlled case series, which is when you use reference time just for a short period of time in between doses, during which no other dose could occur. So quite complex. Or we can use these extensions of the self-controlled case series that Anders mentioned as well, which are based on estimating equations and correct for this bias as well. So lots of different options, but I would think it's fair to say that they're not so commonly used. So what we were interested in was to explore in this context, well, what is the impact of using these different study designs? So we had the same core design that Carlos just presented really nicely, the SERI using pre-vaccination time as the reference. We then used an SERI using only post-vaccination time, which in our setting is very similar to this truncated SCCS. We used a standard SCCS and this extension of the SCCS as well. So the key concern, as I mentioned, is this violation of the event-dependent exposure assumption. And we think that if we have this violation, we will see an overestimated harm using the first design and the third design, but probably we were most concerned about the first one. So Carlos already presented the methods. We used lots of different data sources, and we've already heard about how we analyze this data today. We had some design differences compared to the main study just for pragmatic reasons. So we excluded people who received different brands of vaccines. And we also didn't consider third and fourth vaccine doses, and that's because the numbers was very small. But if they occurred, then we excluded them from the reference time. So this slide just shows the designs in more detail. So at the top, you can see the, I don't know how to, So you can see the SCRI, so we have the risk periods after vaccination and a pre-vaccination control period. We have the post-vaccination SCRI with risk periods after vaccination and the control period after vaccination. And then both of the SCCS where we have control periods, which essentially is all time that wasn't risk time. And in all of the designs, we implemented pre-exposure periods of 30 days or so. Okay, so we ran all of our analyses using the SCCS package in R because that allows us to implement this extension of the SCCS automatically. We then meta-analyzed our results across databases and presented just one summary estimate per vaccine brand and per design. And we assessed agreement between these designs quite informally, so we essentially just considered would our conclusions have changed if we had used a different study design. Okay, because we don't want to just look at what happened in our specific study, we also ran a simulation study, and this is work led by Yvonne Martin. So I'll do my best to try and explain it, but essentially we simulated a case series with different sizes, with different effect sizes. And then an important design aspect of the simulation study was that vaccinations could only happen in kind of the middle of the simulated time period. And I'll come back to why that's important later on. And then we introduced this bias. So after each event occurred, we then lowered the probability of the exposure happening with a certain probability. And I'll speak particularly about the impact of this on the bias in the different designs. Right, so results. So this essentially shows the results from the first dose unadjusted analyses. So you can see the vaccine brand here on the left. We have each of the designs and then the summary estimate from the meta-analyzed results. So you can see, first of all, that we have pretty good agreement across the board between the SCRIs using both pre- and post-vaccination time. I would say that they're pretty close overall. For Moderna, so something interesting here is that for the SCRIs, we actually found more sort of extreme or a greater harm for the SCCS, which was a little bit unexpected, but the confidence interval was still quite wide. For for dose 2 results, unadjusted, we found pretty good agreement. You can see the harm here for Moderna and Pfizer for dose 2. Adjustment for calendar time. So this is something I'm interested in. If you've fit these models using the SCCS package, please come and chat to me about how we can best adjust for calendar time, because what we saw was this huge inflation of confidence intervals. We think this is probably because of a collinearity issue. It's quite tricky to fit a calendar time trend when you have very short time periods. So essentially, none of the conclusions really changed when we adjusted for calendar time, but we saw this huge inflation of the confidence intervals. And this was the same for dose 2 as well. So you can see similar, reasonably good agreement between the doses, but really wide confidence intervals, particularly for the SCRI methods. This is a lot, and I know it's late in the day. This is results from the simulation study. So I thought we'd focus in on just one scenario. So this is kind of a middle strength of this biasing process. Essentially, so the dotted black line is no bias in the rate ratio. Anything above it is an upward bias in the rate ratio. Anything below it is a downward bias in the rate ratio. And there's two things of interest here. So in the black solid line, which you can almost see, we have the standard SCCS without a pre-exposure period. And in the orange line, we have an SCCS with a pre-exposure period. Okay, so when we saw these results, I mean, I'm not sure if you're reacting like this, but we were very surprised. And the reason for this is that it's essentially the opposite of what we expected, right? So kind of presumed knowledge when using an SCCS is that when we have violations of this this assumption, we see an upward bias when we don't correct for it, and we can correct for it using a pre-exposure period, particularly when it's limited, like it was in this scenario. And this is something that has been sort of quite widely known and described in the literature for the past 10, 20 years. So we were trying to work out what was really going on here, and I'm going to try and explain it to you. I know it's late. But yeah, so essentially this shows the standard setting for a self-control case series. And what we think matters here is how the event impacts vaccination, right? So if the event contraindicates vaccination, this kind of person that you see on the slide here will just never make it into the case series, okay? So then you kind of get this bias in the expected direction because you are underestimating the relative risk in the period before vaccination. But if you just delay rather than contraindicate, then you just have this. So the vaccination just moves later on in time. So unless vaccination is delayed kind of until the end of your observation time, so that case falls out, if you like, of the case series, then the total amount of reference time you have doesn't change. The total number of cases you're including is not changing. So removing parts of your reference time by including a pre-exposure period will actually overestimate the baseline incident and underestimate your relative risk, right? So we think actually that we should see an upward bias, but we're seeing a downward bias instead. So to quickly conclude, from the empirical analyses we did when we compared these different methods, I think our conclusions are largely reassuring. The SCRI and SCCS found largely similar results, or at least not results that would lead us to come to different conclusions. And this worry we had that the SCRI using pre-vaccination time in the reference window would lead to an overestimation, that didn't seem to be the case, right? So that's reassuring. For the simulation studies, I think there's some really interesting implications, right? So there's been this kind of standard rule that you see this upward bias, potentially we had it referenced earlier as well, and I think that's not always the case. You have to consider how this biasing process is operating within your self-control case series. And we found this interesting thing that using a pre-exposure period might actually not correct for a bias. The standard SCCS as is might be the unbiased option when you're in the scenario when you're still observing all the exposures. But I think there's a lot of future work to be done to understand how the impact of these different biasing processes operates in the SCRI setting, and I think we really want to understand this in a little bit more detail before we make any recommendations around how we should use this in the future. So I think, yeah, to conclude, I think this just really, for me, highlighted the value both of doing sensitivity analyses. I think we feel more confident in our core results having done this, but also of doing simulation studies, particularly of something you think you might already know, or that's an established fact in literature, because certainly for us, we found something quite unexpected. So I think it shows the value of that.
Thanks, Anna. That's quite a lot to take in a short time. Any questions? Oh, yeah.
Yeah, not a question, but actually something that popped in my mind now. Like we are doing some subsequent studies on like the prognosis of myocarditis in persons that had a myocarditis to see what happens.
Yeah.
And actually what we're seeing is that most of them are vaccinated again. So it may, it doesn't contraindicate the vaccination, but actually it may be delayed. So that's supportive of your thoughts, I think.
I think so, and I think we saw something that's potentially quite specific to COVID vaccines as well, because we had this huge quick uptake of vaccines, right? So we're in quite an unusual scenario where we actually have a lot of people getting vaccinated quite early on during our observation period, and then we can follow them later on. So I think maybe some of the conclusions that we're finding are specific, as you say, to this specific clinical scenario, to COVID vaccines where we have this uptake, and might differ when you're studying something like a routine vaccination.
Just a point which Miriam has said. We looked into this, and there were different recommendations in different countries. Some countries said if you had myocarditis, pericarditis, never take the same COVID vaccine or any COVID vaccines. Other countries were more relaxed. And also there were differences in the decisions. As people got confident that these were young people, they don't get any harm, their echocardiograms and ECGs are okay, some of them started to get vaccinated. So there may be an opportunity for somebody to look at the various scenarios which happened in various parts of the world and enhance the self-controlled case series depending on the strategy in the countries, whether they got vaccinated afterwards or not.
Yeah, that's a really interesting point, actually. Obviously, I'm kind of hiding all of the country-by-country variation by just presenting the meta-analyzed results. We didn't really see anything that kind of variation, I think, in country by country, but the challenge we had is that in each individual country we had so few number of cases that by that point the amount of uncertainty around it made it quite difficult to compare. But I agree with you, that is quite a nice kind of natural experiment of it.
All right. I think we'll close this presentation and discussion. Thanks, Anna, again. And then the final presentation of today and of this session by my colleague Sophie Bots, assistant professor at our division in Utrecht. And Sophie's going to talk about a review of the different studies that have been done on COVID-19 associated with vaccination, and if we can sort of learn from different methods and how they explain the results. So please, Sophie, go.
Yeah, thanks. So, last talk of the day. I hope you are all still here with me, because I would like to welcome you to your first day of your postdoc on vaccine safety. This was me 2 years ago when I started in this project, fresh out of my PhD, very excited. And the first thing that I was asked to do was myocarditis and pericarditis and COVID vaccinations. Go study. I think some people mentioned the need for speed, and I think Carlos said it was September and we had to have something like results to the EMA by December. So it was like a massive, no pressure, it's all gonna be fine. So let's do a study. And the first thing I did when I came into here, I was completely new to vaccine studies. So I thought, okay, what do I do? Where do I start? The nice thing is a lot of people, of course, have worked in this field for a long time. And there is this very nice framework for study design selection if you want to do rapid safety monitoring of vaccines. So that's where I started, and they had a very nice kind of decision table in that paper where they said, well, first you need to think this is health outcome of interest, the onset. What kind of onset do you have, and is misclassification, can you ignore it or not? I think myocarditis is a pretty well-defined outcome. It's a very short duration between the exposure and the occurrence. Then we need to think of confounding both invariant and time variant. So invariant, we've already heard about sex and age and all kinds of things, so we can't ignore that. And I think seasonality here, like with the COVID pandemic, we also cannot ignore it. So where do we end up? We end up with a selection for case-centered analyses, which includes the self-controlled risk interval study. So as you already know, that's exactly what we did, including also a cohort for absolute risks. But I was mostly involved in this part. So it was great, and then I had to write the discussion. How does it compare to the literature? And I think today already you have shown you that there has been a lot of work done, and it's all been quite different in their approach. So when I had to write the discussion session, I looked into the literature, and the first thing that I saw is that if you had different studies with different countries already, they all chose different ways of running these studies. So we had case controls, we had cohorts, different types of cohorts, different types of self-controlled studies. So how do you compare these? Because not only did this differ, they also had different risk window lengths, so either 7 days or 28 or both. Some of them had dose-specific data and some of them did not. And then if you looked at the different cohorts, they used different specific analyses choices that they made. So then when I tried to make sense of this, color coding the things that I think should be the same, you can already see that there is some variation even within the same studies that use different designs. So we, here you can see that the Danish, they had the same designs. But even things that should be the same sometimes vary really greatly depending on
reasons. And I thought, well, what are these reasons? Can we kind of look into this and think, can these differences be explained? Maybe study design itself or other considerations. Let's do a systematic review. And for this, I got a nice student, Bram, who did this for me as his bachelor thesis. So these next slides are his work. So first we searched the literature, then we screened and we analyzed. So for the search, we had a search term, which I think is too big here, but just to show you that we had a lot of terms for myocarditis and all the different vaccines that could be used, the COVID vaccines. And we also had some specific considerations. I hope you can read them, actually. But there needed to be some kind of COVID vaccine. The comparator was either unvaccinated individuals or person times, just to make sure we could compare, because there were also lots of studies that compared different vaccines between each other. The outcome had to be myocarditis, not a combination. There were also studies that used myopericarditis together or something like that. And it had to be an observational study, so no randomized trials or things like that. Then we screened. For this, we used the AS Review tool, which is a super nice tool where you can put in all your information, and then machine learning software actually supports you in sorting up and down relevant studies based on relevant and irrelevant publications that you decide a priori. So we had 5 relevant publications that were the ones that I showed in the table earlier that we knew we were interested in. And also, for example, we included a case report as an irrelevant publication or a randomized trial. And then this machine learning software sorted it for us. The nice thing is then you don't have to screen everything. So we defined a priori a cutoff criterion. Bram was going to stop screening when he screened 33% of all papers. And based on that, for me, I could stop screening when I had 50 irrelevant consecutive papers. And after that, we did full text screening, which was done kind of the standard way, because AS Review does not support that. As I said, screening was done both by me and Bram. And then we extracted some information, mostly on things that could differ between studies. So the design, population, the country, the age, vaccine types, but also risk windows, confounders, and the estimates that came out of these studies. We then did a meta-analysis using random effects models, and we stratified these specifically by things we thought might explain heterogeneity, such as the study design and also the duration of the risk window, which was divided into these 2 categories. We found about 1,000 papers, and 37 of those were relevant, and in the end we included 12, because even in the full text we found some that, for example, had myocarditis, pericarditis as one event. Some of them had no confidence interval, so we couldn't include them. And sometimes we also still found, for example, there were some studies that were done in people over 70, and we felt that that was not a very representative population to include in a broad comparison like this. Very busy slide. These are the studies. What I just wanted to highlight here is that there's a lot of variation. So you have country variation, you have study design variation, you have the type of population or data set that was used, from what age people were included in the study, the follow-up days were different, how myocarditis was defined, which I think this is the study that Anders maybe mentioned earlier that has very specific definition, and also which confounders were adjusted for in these different studies. And what we saw here is, interestingly, I only show Pfizer and Moderna because we saw a risk there, is that if you look for Pfizer, it seemed as if the self-controlled group had kind of similar to the cohort, at least in the first dose, and it was a bit more, less extreme, if you want to say so, than the case control. And it's kind of the same for the second dose, except that in the case control and the cohort, you see much more heterogeneity than is in the self-controlled studies. And I think the same thing was seen for Moderna, where the case control was actually, especially here, very extreme and much more extreme than what the other 2 study designs showed. Then if you stratify by risk window, so this is still putting all the study designs together. But what was interesting, I think, here is especially for the second doses, that if you have this 28-day risk window, you actually get a less strong result than if you have the more extreme risk window. And you see that here as well, which might have to do with some biological variation in like when it occurs and if you maybe mask some of the effect. I think also what Carlos showed when we did our sensitivity analyses, that this pattern may change and maybe most of the events happen earlier on and not in the later days. So what does it mean? Several sources of variation exist. I think study design could be one of them, as we see that these different, even though the message maybe doesn't change, especially for the case control, we saw some very extreme estimates, which may have to do with, oh, that went very fast, may have to do with confounding, but maybe also with the underlying estimates and thing you're trying to assess with these different designs. Of course, there's always the chance that it is effect modification based on the population that was studied, a biological effect based on which risk window you choose, or maybe the definition of myocarditis that was used and the degree of misclassification that can be expected there. So, still a lot to do. So what is next? I would like to welcome Tran, who is my PhD candidate, to the first day of her PhD on COVID vaccine safety. And her systematic review that she is going to do, which is going to build on the work that I have just showed you, but then really expanding on it by not only looking at myocarditis, but also the other complete list, completer list of adverse events of interest, depending, of course, on what is published in literature. We will include a bias assessment using the Robbins eye tool to see for these different studies and study designs, what is the quality of the work that has been done. We would like to dive into these axes of heterogeneity a bit more, and that also would include meta-regression or other ways to kind of see and quantify if we can see how much of the heterogeneity can be explained by different differences between studies. With that, I'd like to thank you for your attention.
Thanks, Sophie, and good to learn that there's always more work to do for people. Questions from the audience? Vera? Let's go over here.
Thank you. Maybe not in your presentation, but before I was just thinking when we look at different types of vaccine and myocarditis, the non-mRNA vaccines, they're kind of a negative exposure control, right? That could be used. And I'm wondering in terms of myocarditis and when we look at cohort designs, how much do we think of maybe differential misclassification is happening at this point?
That's a very good question, and I'm not sure if I'm the one best equipped to answer that.
Or any of it, is any of the effect due to, I think it's probably real, but maybe could some of it be explained of differential misclassification, and if yes, do we care?
Well, I think what I took mostly, I think from what has been presented here, and also what I took from this is that I haven't looked into misclassification. I think there's some work being done in our group that is looking into that, but I don't have the details on it. I think the reassuring thing I saw from this is that at least everything goes in the same direction, so that's, I think, also what Anders said. But for future, also maybe going back to communication about risks, it might be nicer to, yeah, that's why I wanted to figure out like which one are some of them maybe over or underestimating the risk, and especially this French case control study that I saw that had like relative risk of 30. That's a completely different message you're telling people about safety of your vaccines than if it's like 2 or 3. So I think there would be something I would be really interested in looking into.
It also depends on the absolute risk value.
Yeah, of course, yeah.
First Saad in the back.
Thank you, that's very nice.
I have was first, sorry.
Sorry.
Yeah,
I have a conflict of interest here because I developed pericarditis and pericardial infusion, and I wasn't below 30. In your adjustment for confounders, did you find any risk factor for developing myocarditis and pericarditis after the mRNA vaccines or the AstraZeneca vaccine? Is there a risk factor?
Well, this was a systematic review, so I didn't adjust myself. I do know based on literature, and I think what we also saw in earlier studies is that the pericarditis, we didn't see a very strong effect. What I saw in literature is that it was more common in people over 30 who also had multiple comorbidities or other health-related concerns. And I think there was also slightly increased risk in women, but this is purely based on the case reports that I have read.
Thank you. Very nice work, very nicely presented, and it's very useful what you're doing for lessons learned. And what's going a bit fast, but when you presented all the relative risk odds ratios with the confidence interval, my global feeling was that they all overlap, basically, whether they were close to the nil or with the higher incidence. And then, on the other hand, your sort of trigger for this is say, well, we see different results from different studies. I'm not so sure that this would have been my feeling. Now, but it was going a bit fast. So in the end, do you have evidence that these studies were really providing different, not different estimates, but different conclusions? And one way to tackle that, and in terms of lesson learned in the future, maybe you should see what decisions were taken from each of the study. Maybe there was no decision from each individual study, but you could probably try to find some regulator or retired regulator who could look at the study and say, this is the decision I would have taken. And maybe even more interesting, I'm just thinking aloud, you may go into your set of studies and take some random samples of, for example, 2 studies, so you would have one replication, and then again ask what would be the decision from the regulators, or like simulate the PRAC or something like that, because it's no longer pharmacoepidemiology, but it means, because basically if the decision would have been the same, then it means the design, of course, it's important, you see variation, but at least we would have confidence that we would have basically have the same decisions, and maybe the design is not, it is important, but we would still have had the same conclusion.
Yeah, no, I think that's a very good addition. I think one of the things we wanted to methodologically look into with Tran is also simulating this and trying to see if there's any differences in important bias things. But yeah, I don't know if the decision would have changed. I was just, as an epidemiologist, very surprised sometimes that I could see a risk of 1.5 and a risk of 30 in 2 different studies of the same, presumably the same effect. And I was trying to figure out how that works, and maybe as a lessons learned for future work, seeing, for example, we know the SCRI is very fast. Would it be a viable option to do that first and cohorts later that I understand take more time? So I was more thinking in that direction, but I'm really taking aboard your suggestion of...
Yeah. So, yes, it's surprising to see 1.5 and 30, but when I see that, I would immediately look at the confidence interval, and I think there's too much importance given to p-values, and this is significant, this is not significant, and I've heard to the conclusion that there were difference between those or whatever, because one is significant but the other is not, but the confidence interval was overlapping, so I'm not sure this is the right conclusion statistically speaking. So, okay, fine, there are estimates which are sometimes all over the place, but if you look at the confidence...
No, I wouldn't say they were statistically different. It was just the spread of it that surprised me. Yeah.
Thank you.
Thanks.
Maybe just one question, and I have to apologize because I'm not an epidemiologist, I'm only a biologist. So I was wondering if you look to all these parameters like pericarditis, do you know if there are any specific biological parameter that could explain that? I'm thinking to CRP, to the level of IgG and things like that. Do we have any clue to make a relationship between all this observed epidemiology, observed phenomenon versus biology?
So I'm just a simple epidemiologist and not a biologist. I know data on that exists, and I don't know if clinicians in the room know more, but I think there has been work on that showing why the myocarditis and not the pericarditis signal is associated with the vaccine. But I don't want to do any conclusions on that because it's not my field of expertise.
Last question.
Yes, it's not exactly a question, but a thought that came to my mind, because from the graphs you built from your review, I thought that I saw that there's a kind of systematic pattern that the lines follow depending on the method the studies used. So maybe it would be a great exercise to try to quantify this systematic difference. I don't know if the Blunt-Talman method or something like this could work, but it would be great to quantify this difference, because I anticipate that in upcoming outbreaks we may face these different designs, and to draw conclusions it would be really nice to anticipate this quantitative difference that we may expect. So this could be a nice methodological exercise.
Thanks.
Thank you for your presentation.